Single neuron draws a straight line. That's useful, but limited. What happens when you connect thousands of them? The lines start combining into curves, surfaces, and boundaries complex enough to recognize a face or understand a sentence. This is how AI actually works. Part 2. Neural networks. In Part 1, we built an artificial neuron from scratch. Inputs, weights, bias, activation function. It takes in numbers, does a calculation, and outputs a decision. And we saw that what it really computes is a straight line through the data. Everything on one side gets one label, everything on the other side gets the other. And we hit a wall. Some patterns can't be split by a single straight line. If the data curves or spirals or forms clusters, one neuron is stuck. So the natural question, what if we use more than one? Take two neurons and give them the same inputs. Each neuron has its own weights and its own bias, so each one draws a different line through the data. Two neurons, two lines. Those two lines divide the space into up to 4 regions. 3 neurons, 3 lines, even more regions. Each individual neuron is still just drawing a straight line. That hasn't changed. But the combination of multiple lines creates regions that no single line could. Think of it like cutting paper with straight scissors. One cut gives you 2 pieces, 2 cuts up to 4, 3 cuts up to 7. Each cut is straight, but together they carve complex shapes. We don't just toss neurons into a pile, they're organized into layers. A neural network has at minimum 3 kinds. The input layer, that's just your raw data. For our student example, hours studied and hours slept. 2 values in. The output layer produces the final answer. Pass or fail. 1 neuron with a sigmoid, outputting a probability, and in between, hidden layers. This is where the real work happens. Each hidden layer is a row of neurons. Every neuron in one layer connects to every neuron in the next layer. The inputs feed into the hidden layer. The hidden layer feeds into the output. You can have 1 hidden layer, 2, 10, 100. The more layers, the deeper the network. That's where the term deep learning comes from. When data enters the network and flows through to produce an output, that's called a forward pass. Let's trace one. Our 2 inputs, 6 and 7, enter the network. They reach the hidden layer. Each hidden neuron receives both values. Neuron 1 multiplies by its weights, adds its bias, applies real U. It outputs 2.4. Neuron 2 does the same with different weights. It outputs 0. Rel U killed the negative value. Neuron 3 outputs 1.7. Now those 3 outputs in 2.4, 0, 1.7 become inputs for the output neuron. It multiplies, sums, applies sigmoid. Final answer, 0.92, 92% chance of passing. Data in, answer out. That's a forward pass. What are those hidden neurons actually doing? Each one draws a straight line in the input space, just like a single neuron would. But they draw different lines. One might learn to separate studied a lot from didn't study enough. Another separates well-rested from sleep-deprived. A third captures a diagonal, some combination of both factors. The output neuron then combines those responses. It learns to say, activate when neuron 1 is high and neuron 3 is high. That combination creates a region in the data, not a single line, but a bounded area. The boundary has corners and edges. It's not smooth, but it's already more complex than anything a single neuron could draw. One hidden layer gives you regions made of straight edges. What about 2 hidden layers? The second layer takes the outputs of the first and combines them again. Regions get merged, intersected, subtracted. The boundaries get more intricate. 3 layers can approximate curves, create holes, form islands in the decision space. Remember the XOR pattern from part 1? The one a single neuron couldn't solve? A network with one hidden layer of just 2 neurons handles it. 2 lines that together carve out exactly the right regions. Concentric rings? 2 hidden layers. Spirals? 3. Each layer builds on the layer before it, combining simple patterns into complex ones. In 1989, George Cybenko proved something remarkable. A neural network with just one hidden layer given enough neurons can approximate any continuous function to any desired accuracy. Any function. Classification, regression, probability distributions. All of it. This is the universal approximation theorem, but there's a catch. Enough neurons might mean millions in a single layer. That's impractical. In practice, deeper networks with fewer neurons per layer work much better. A network with 3 layers of 30 neurons often beats 1 layer of 1,000. Depth gives you composition. Each layer builds abstractions on top of the previous layer's abstractions. That's far more efficient than brute forcing it with a massive single layer. Modern AI goes deep. AlexNet, the model that kicked off the deep learning revolution in 2012, had 8 layers. VGGNet pushed to 19. ResNet in 2015 went to 152. GPT-3 has 96 transformer layers. Each generation keeps going deeper. Why does depth work so well? Because each layer extracts increasingly abstract features. In an image recognition network, the first layer detects edges. The second combines edges into textures and corners. The third finds shapes. Later layers recognize eyes, wheels, windows. The final layers identify whole objects and scenes. Nobody programs these features. The network discovers them on its own, layer by layer. Quick vocabulary. The number of layers is the network's depth. The number of neurons per layer is the width. A network with 2 inputs, 2 hidden layers of 64 neurons each, and 1 output is written as 2, 64, 64 on 1. The connections between layers are edges, and each edge has a weight. The total count of weights plus biases is the parameter count. When you hear GPT-4 has 1.8 trillion parameters, those are all weights and biases in neurons. Same building blocks we've been looking at. The same multiply-sum-activate pattern from part 1, repeated 1.8 trillion times. Here's what we covered. Neurons are organized into layers: input, hidden, and output. Data flows forward through the network. That's a forward pass. Each hidden neuron still draws a straight line, but layers of them combine to form complex decision boundaries. With enough depth, a network can approximate any function. Straight lines all the way down, but the composition creates curves. But we've been assuming the weights are already set. We haven't explained how they get there. How does a network with thousands of neurons and millions of connections find the right weights? It can't try every combination, like there are more possibilities than atoms in the universe. It needs a smarter strategy. That's part 3. How neural networks learn.